There we go. All right, welcome to this problem session of the HoTTEST School 2022. This is the problem session for the third exercise sheet, and it lasts an hour. I will try to get through the problem sheet, but I will prioritize any questions that show up. I think the solutions, there are solutions for the problem sheet, so I think it's more important to prioritize any questions that come up. I suggest, like, as you can see, I'm just sharing my, like the portion of a screen that I'm going to write on. I suggest you put the exercises maybe side by side so you can follow along and understand when I'm referring to certain questions that we're on the same page. Okay, and feel free to interrupt me with any questions, write in the chat. I have the chat on my screen here. And yeah, we'll see how this goes. So I'll just jump in and start with saying how I would solve exercise 1. And so exercise 1 lets you know that there is a, gives you a type A. So let me just write this out. A is a type. And then you're given 3 elements of A. So X, Y, Z, and A. And we're supposed to show that path inversion distributes over path concatenation. And that's an informal phrase, which the formal statement is what I'm about to give you. So we're going to give a term of the following type. So for all paths X to Y in A, and all paths Q from Y to Z in A, we want to show that if I compose P and Q and then invert the result, this is equal, meaning that there's a term of this identity type to if I first invert Q and then I invert P and I compose. Okay, so to construct an element or a term of this type, it's a dependent function type, so I'm gonna take a parameter and I'm going to try to construct something in the like the codomain, which then varies over the parameter. So let P be a path like this. Then we need to give a term of the following type. So I've just assumed that I have some P now. And
Q should still be from Y to Z, right?
Oh, sorry. Yeah, you're completely right. Thanks. So Y to Z, and A. And yeah, the subscript of that equality, it's A here. The big one, you're right. So let's write out the type here. So this is this is an equality of paths. So P composed with Q goes from X to Z, but then we invert the path. So this is a path from Z to X in A. So it's an identity type in an identity type. And I'm going to say identity and path interchangeably. That's just how I am. I'm not alone in that. And I should also say this at this point in the course, we're moving to working a bit more informally with type theory. So I'm not going to write out a proof tree for constructing this term. Rather, I'm going to more informally, but rigorously still, apply the elimination principles of that, like, to give a more informal type theoretic proof. So we're constructing an element of this dependent function types. I assume a parameter, and now I need to give you the output. So I need to give a term of this type. But by path induction on P, it suffices to give a term when P is equal to REFL. So by path induction on P, we may assume that P is definitionally equal to the reflexivity path at X. Then the above becomes the following. So first of all, then X and Y become definitionally equal because we've contracted the path P. So we need to give a term of the following type. Now I'm writing X here to Z because Y and X are definitionally equal. And I'm putting reflexivity in for P in the above expression. And let me just comment here, just note that reflexivity, when you invert a reflexivity path, you can just drop the inversion because it inverts to itself, and that's going to come up in just a second. So now we need to give a term of this dependent function type. And again, I'm going to introduce my variable. So let Q be a path of this type. And then I need to produce something in this inner path here. And again, by path induction on Q, note that Q is not a loop. It's a path with free endpoints. So by path induction on Q, it suffices to, or we may assume that Q is reflexivity at X. So we may assume that Q is the reflexivity at X. The above becomes, then the above becomes so reflexivity at X. That was from the previous P, and now I'm plugging in reflexivity at X for Q. Reflexivity at X inverse, reflexivity at X inverse. Yeah, so there's a question in the chat, how do we prove that inversion is equal to the reflexivity of itself? And you define inversion by path induction. And so you send reflexivity to the inverse of reflexivity, which is going to be reflexivity. And so the computation rule, as Ian Ray is saying in the chat, it comes from the definition. You get a computation rule which says that reflexivity is sent to reflexivity. So that's not something you prove. It's by definition or by construction. So now we've inducted on Q, and the goal became the following, what I've written here. And I'm gonna move a tiny bit. So I'm gonna, yeah, here we are. So the goal becomes what I've written out here, but so this just computes. If you compose two reflexivity paths, this is, so this becomes reflexivity and then inverse, but it just computes to reflexivity. So let me write it a bit better. So this is definitionally equal to just reflexivity. Since composition, concatenation, and inversion just sends reflexivity to reflexivity. And same here, you can drop both the inverses and then you get reflexivity composed with reflexivity, which is just reflexivity. So then I can take reflexivity at the reflexivity of X, which is a path from reflexivity to itself in X equals X of A, is such a term. So I've used path induction twice, and I've given a term of the required type. The induction principle then gives this dependent function type that we wanted at the start. Yes, sorry, the triple line equals is the same as the dotted equals we've been using in the lectures. it's definitional equality or judgmental equality? That's a very good question. So there are various conventions on this. I should probably use the dot equals, and I think it's used in the exercise sheet.
I think the reason we're using it is because the AGDA inconsistency, right?
Right. Yeah, maybe that's the
because in
historical
AGDA, the
reason.
triple equals is the identity type.
Yeah, right. Okay. Yeah, so you can't yeah, so that notation is used for something more important. I see. Okay, so that concludes question 1. Shouldn't the answer be in something? So somebody is asking in the chat, if you're using an elimination rule, shouldn't the answer be in something? And that's one way that's true. So the answer is it's a dependent function type, which is the abstraction of in something. So when you do in something, you have some variables in context, and you get in something, which is the actual element. But when you abstract over those variables in the context, then that's the dependent function type you get. And if you unroll what I did in terms of like literally writing out the induction terms, then you do get in something appearing. So there's no discrepancy, really. I hope that answers satisfactorily that question. Now I saw there was a raised hand, so I'm gonna. There's a raised hand. Does Ian want to speak up, ask his question?
Hello. Sorry,
hey,
my microphone's
I
muted.
can hear you. Yeah.
So I'm a little confused as to like when we're allowed to do path induction. Can we just assume, like always assume a term of the identity type is REFL, or is it like more complicated requirements than that?
It's more complicated,
Okay.
but not much more complicated. So as long as one endpoint of your path is free, you can assume it's REFL. That's the answer. As long as it's not a loop. We'll get more to why that is in question 4. But what you need to check every time you do path induction is to check that at least one endpoint is fixed. And if one endpoint is fixed, well, then you're contracting the path to that endpoint.
Sorry, this might be a very simple question, but what do you mean by the point being fixed? It's already got a value in the context, or? For example, if you're trying to prove something like for all p from, so if x is some variable a in context, x is some variable type a in context, and you're trying to prove something like this, and there's some dependent function here, you can't use path induction because p is a loop. So cannot use path, and since p is a loop. So that's what I mean when I say it's a loop, or both endpoints are fixed. It could also be, it could also be their actual values. Let's see. So it could be like here, x is a variable of type A, but x could be an actual, I mean, the difference between a variable and a value here is sort of, doesn't really matter. So x could be something very concrete, a concrete value, and you wouldn't be able to path induct on it. It could be in the natural numbers, x could be number 2, for example. Okay, there's a bunch of questions in chat. I'm gonna see if I get to this. Yeah, the in stuff is hidden in the English. And inversion and concatenation are defined in the lectures, lecture 3. So REFL is a loop, that's true. Yeah, it doesn't contradict anything. And what I mean is such a term. I mean, in the proof, we need to give a type of a certain term. The term, so when after taking taking the variable q into context, we need to show something of this form, and then I induct on q. So I plug in q or refl for q, and I need to give an element a term of this type, and I'm saying reflexivity at the reflexivity of x is such a term. So that's I'm asked to supply a term, and it is such a term. That's what I mean. So if you have 2 equals 2, you cannot make that become refl. That's true. Now we're going to show later in the course that for the natural numbers form a so-called set. So any path, any loop at 2 is judgmentally equal to refl, but it's not definitionally equal to refl. But this will be a theorem. It won't be some basic fact. It will be something we have to sweat to prove, like work hard. So yeah, it's not a.
So I just want to say something just to clarify.
Yeah.
I think you said not judge. You said it would be judgmentally, but not definitionally. And I think you meant
propositionally.
Will be propositionally. Okay.
Thank you. Yeah. If I made that slip of tongue, I meant propositionally. Yeah. Sorry. No, that was apparently confusing people in the chat as well. So yeah, we will be able to show that any path from 2 equals 2 to 2 in the natural numbers is propositionally equal to reflexivity, but not definitionally or judgmentally. Okay, so let's move on now to exercise 2.
Maybe I have a request. I mean, can we write some of the induction principles we used in the proof as a sketch of formal proof tree? I mean, in order to somehow make a contact between this informal natural language notation and this horizontal line proofs. I mean, can we do something like this?
Let's see.
And maybe I understand that the proof tree actually can be very huge.
Yeah. So the proof tree here will be substantial. I don't want to write it out.
Okay.
I mean, it's good to think about both, and we'll actually be thinking about both in the next exercise. So maybe that will help a bit. Okay. And it's just something that you get a feeling for what operations are allowed, which operations aren't. Yeah. Okay. So. Right. No, so there's a comment in the chat that the proof tree would also need to validate that refl is its own inverse. That's not true, because by definition, refl is its own inverse. So this will just compute. It's not something you will supply. That's actually just a reduction step that you can do. It doesn't need a horizontal line. Okay. It would be a beta step, for the beta reductionists out there. So are eliminations and other rules just shortcuts for proof trees? Yeah. I guess I agree with that sentence. Just like, I mean, if you're doing mathematics in set theory, everything you're saying is a shortcut for a set. But you don't think of it necessarily like that. Okay, so now for question 2, we're given 2 types, A and B. So A and B are types. And we're given this elimination principle for the product type. And we could either just
say what product types are and give their elimination principle, but we can also, since we know what sigma types are, we can define product types as special cases of sigma types. And then we get the elimination principle just as a special case of the elimination principle for sigma types. So that's really all that's happening here. And the elimination principle says that if you have a type family over the product, and you know where each canonical element goes, or where each pair of elements A and B goes, well, then you get a dependent function into this type family. So the first part of this exercise asks you to define the two projections. And the projections are non-dependent function types. So they tell you where, so this D, the D of Z is not going to be dependent on Z. It's just going to be constant as C changes. So that's what it means that when I say constant type family. Okay, so we're going to define the first projection, and I'm going to use the elimination principle for that because that's what the exercise is asking you to do. And I'm going to write gamma here, but it's not some abstract ambient context. It's literally just containing that A and B are types. So let me define gamma. Maybe like this. So that's gamma says that A and B are types, and so we can consider Z in their product. So now I'm going to start by giving this D, and the D is just going to be A for every Z, so it's constant. And then I need to supply something on the right-hand side of this rule. So I have A and B like this. And now I need to supply something of the type A. Well, I'm just going to take the variable A. And using this as my input to the elimination rule, cross elim, I get an output here. C A cross B. And I get this induction term. So A is usually how I would write it. Z like this, and in A. And this is what we will call PR1 of Z. Okay. Right, so I see there's a raised hand. Let me just first answer the question in the chat. So the chat is reacting that in the second premise in the exercise, they want another pair of parentheses, which they're formally correct, but this is just how we write it. So, so D A B is equal to D A B. Okay. Why did I write A instead of DZ? So the elimination principle is an abstract thing where you need to, so D is some abstract type family over Z. And if I want to define a concrete function using it, then I need to say what DZ is. And here I'm saying that DZ is A. So I need to supply something concrete. And I know that A is a type, so I can form this judgment. If I wrote DZ, there is no D. So I can't write that. Okay, so there was a raised hand. That person can just go ahead and speak.
Hi. So the conclusion of that elimination rule you just wrote uses the variable little a.
Yeah.
It doesn't appear in the context,
right.
which I'm not sure what's up with that. Is that okay? And if so, why?
So formally, this is a sleight of hand. So formally, A depends on A and B here. it depends trivially on B, but formally it depends on B. So when you write it here, you bind all those variables. So you bind A and B, and then you return A. And then there's Z. So there's an implicit, you're binding the dependence, so sort of carrying it with you.
Int takes a function type as opposed to just a term of type D of whatever.
Yeah, it takes, so this tells you where the two elements of the pair goes, A and B. And so this is the it takes a function type, yeah.
Okay, cool, thanks.
And this is what we're going to define as PR1 of Z. So that's the first projection. All right. And the second projection is similar. You replace A with B, and then you replace A with B, with lowercase and capital, respectively, or irrespectively, actually. So that gives you the second projection. And now, for the second part of the exercise, we're asked to prove a certain statement, which I'll remind you. So now we want to show that for all pairs, or for all terms of the product, that Z is equal to its first projection coupled with its second projection. Okay, and to show this, we're going to use the elimination principle that we were just using in the previous part. Okay, so let's see. So there's a formal way ahead, and there's an informal way ahead. So maybe this will help illustrate the question earlier. Yeah. So let's write out our rule again. And again, gamma is as above, it just contains A and B. And for the type family we're considering, it's kind of, we don't really need to write it out because this here is telling you exactly which type family we're considering. So I'll just copy that here. Z, and that's type, because identity types are types. And yeah, maybe I should add in this identity type in a product. And I don't have space to the right here, so I'm just going to write the next thing on the next line. So now I need to give a term of the following type. So I have A and B and B. And I need to supply a term where now Z is the pair A comma B. And on the right-hand side, I'm applying the two projections. So I need to give a term of this type. Oh, so I didn't leave myself any space for the term. Let's see if I can quickly fix that. Oh. Ooh, great. There we go. Okay, so before we can give a term of this type, we need to do some beta reductions, some computation. And it follows from how we constructed PR1 just up here, that when you actually apply PR1 to a pair, an actual pair such as A comma B, then you just apply this function you passed into the first parameter of int. So it actually just computes. And so I'm going to delete this PR1. I'm going to compute it. So PR1 applied to A comma B is just A. That's just the computation rule you get from the induction principle. So you get A here. And similarly, PR2, this is just going to compute to B. That's just by what we got from the definition. Okay, so now I need to supply a term of this type. And I do have such a term. It's the reflexivity at A comma B. And those are the two inputs to the elimination principle. And so I get out a thing like this. And cross refl. You could leave the variables like this if you want. And then Z here. And that's now of this type. PR1, Z, PR2, Z. And then by abstracting over Z, we get, I'll call it star, and that this is star. So then we get the dependent function type. Okay, so that's a formal, let's call that the formal proof of B, because I used the elimination rule like in a formal way. And well, if you look at the solutions, there's a more informal solution or semi-formal, which writes things out more using English. So I'll let you read that and ask questions if you have any. This brings us to exercise 3. Any questions about 2 before we move on? All right. Then we'll do 3. And yeah, so once again, we're given A and B are types. And we're supposed to construct something of this form. So for all A comma A in A, for all B comma B in B, if I have a path from A to A prime here, so I have 2 paths like this, then I should be able to sort of couple these pairs to create a path between the pairs. Okay. And here we can note that these 2 paths, they're totally independent. So their endpoints are completely independent. So if we call this first one for P and the second one for Q, then if I induct on P, that doesn't affect the endpoints of Q. And if I induct on Q, that doesn't affect the endpoints of P. And this tells us there's no issue in doing like any order of path induction. The only issue that can arise when you do path induction is that by inducting on some path, you collapse things so that some other path becomes a loop. And so here I'm just gonna assume, so
wait, can you say that again? I'm sorry.
Yeah, so I guess I'll come to it in the proof.
Okay, cool.
I'll say it again. So we're gonna fix elements like this, just a sort of formality almost, and now to map out of this product what the elimination principle we saw before, it tells us that it suffices to look at actual pairs of elements in this product. So by the elimination principle, we can take some P and Q in this product here. So that's where P and Q live. And now we can induct on P and Q. And so I'm just introducing them. So we can induct on P and Q since their endpoints are free. Their endpoints are free. And so now let me repeat what I was saying earlier. If you induct on two paths, you need to choose an order always. And it may be that when you induct on one of the paths, the other one gets its endpoints become fixed, or it gets collapsed to a loop. But in this case, the paths are in different types. So there's no way by inducting on one of them that it affects the other. And so the order doesn't matter, and you can be quite informal and still rigorous and valid. And it's just saying we induct on P and Q because there's no danger. So their endpoints are free, and so we induct on them. The goal then becomes since now A is equal to A prime definitionally, and B is equal to B prime definitionally, A comma B in the product A comma B. And we have a term of this type. A term is the reflexivity path at A comma B. And so by the elimination principle, we get an element of this dependent function type. Okay, so let me get to the questions in chat. Can we do that in general for sigmas? I'm not sure what general, what that refers to, if they can ask the question
Might
again.
mean assuming that you can split it into pairs.
Yeah, that's true. You can do that in general for sigmas. There's the sigma elimination principle, which lets you split a general element into pairs, or you just need to consider dependent pairs. So that's true. Okay, here's a question. How are the endpoints of P and Q free since they are bound in the two pi's earlier? Yeah, well, yeah. These are variables. So the endpoints are free. How do I? Yeah, these are variables. So they are elements of your context when you're applying the elimination rule, as opposed to if you had some closed term that was substituted in for the endpoints. So that's the distinction. And as long as the endpoints are independent, we'll be okay, right? Even if A and B are the same type, correct? Yeah, I'm just saying since the types are actually different, there's no consideration to even make. If we had A times A, like two paths in the same type, we would have to check. It wouldn't be very difficult, but we would have to, that would be something we'd have to check that the endpoints are independent. I mean, it's clear since I'm quantifying over 4 variables here. But yeah. Okay, so let's move on to exercise 4. Yeah, well, maybe let me mention this type of map. We'll later see that this map is a so-called equivalence, and it characterizes the paths in a product type. So paths in a product type are just pairs of paths, which is what you would expect. But it's really nice that we don't have to put this in as a rule or some axiom. It just follows from the rules of type theory. So you add in some product type, and then it sort of interacts with the identity types in such a way that you can prove that paths between pairs are just products of paths. So this is the type of This is a principle that is repeated a lot, and it's called characterizing the identity types of a type. Okay, and that's an important thing to do. Yes, exactly. There's a proof in the other direction. So this map is a so-called equivalence. We don't know what that is yet, but we will soon. And it means there's a section. I mean, there's a map in the other direction, which is if you want, it can be a two-sided inverse, but equivalences are quite subtle in homotopy type theory. So they merit their own discussion. Okay, so now we come to question 4, which says the following. So A is a type, and we have some element, small a of capital A. We're going to show that REFL is unique among paths starting at A, but with the other endpoint being free. So this is the sort of uniqueness that REFL enjoys. And this is actually one way of justifying or explaining the elimination principle for identity types. So let me write out the expression we want to show. So we want to show that for all Z, which is a path starting at A. So how do we write that? Well, there needs to be some other endpoint, X, and Z, the second component of Z, is then a path starting at A, but ending at X in A. And for all such elements, all such paths, Z is equal, I should write it the other way. If we consider this, this guy here, that's how we write it, then this is equal to Z in this sigma type. So X and A, well, maybe not, well, Y in A is equal to Y. So this is stating that as a path starting at A, REFL is unique. Okay, so so now let Z be of this type. A is equal to X. Then, so to construct a term of this dependent function type, I assume a variable, and I'm going to show whatever I need to show. And by sigma elimination, I can split Z into a dependent pair. This was what was just asked about. And I can indeed do it. So elimination, we can assume that Z is definitionally equal to some X comma P, where X is an element of A and P is a path from small a to X. Okay. And now by path induction on P, so P is, it starts at A, and what I'm trying to prove has A fixed, but X is free in whatever I'm trying to prove. So X is the free endpoint in this type family that I'm trying to produce a term in. So I can path induct on P. So by path induction on P, it suffices to give a term of this type so after path induction, X comma P just becomes A comma REFL. And we have a term of that type. Which is REFL at this pair. And so we've supplied a term that's needed for the elimination principle. So we get a dependent function like this. Okay, so yeah.
I'm sorry. I just had a thought that I kind of wanted to maybe confirm or see if you agreed with or had something to mention about it. So as we're doing like an informal proof here, writing it in English, it's almost like as you go down the page, it's equivalent to like if you were doing a tree, you start at the bottom and you go up. It's like we're starting at the top with what we're aiming for, and we're going down and we're breaking things down.
I mean, I agree. So if I write proof trees, I usually start at the bottom. I write upwards.
Right, exactly.
So and that's because that's just how most people find it easy to think about proofs. And so in English, we write them from top to bottom, but proof trees are structured from sort of the wrong way.
Well, yeah, I agree with that. But I guess my point is that if you're used to everyday mathematics, you usually don't write a English proof that way. You start with your like base and you move towards the conclusion.
Well, that's what I'm
here. Whereas here we start with what we're aiming for, and we use these principles to kind of reduce things to the whatever is the simple case, in this case, reflexivity. And we know that we can unfold it backwards and get, what we're aiming for. But I just think it's worth mentioning to people that are used to doing math proofs that that's really not how you normally write a math proof.
Well, I don't quite agree with this. So when I write at top here, this is what we ultimately want to show. So I'm just stating what we need to show. And then I'm starting how you would start any math proof by introducing your assumptions.
Your assumption.
And then I'm applying whatever operations I can apply to them. And then I do end up, there's something curious that you end up reducing to some simple case, but that's reminiscent of homotopy theory.
Okay.
That's just the form. That's how most proofs go before homotopy type theory came along. A lot of proofs in homotopy theory go by reducing to a simpler case.
Okay.
So that's more the flavor of that type of mathematics, and it's not just homotopy theory. That's often a style of proof. So I wouldn't say.
Okay. No, that makes sense.
Artifact of type theory. Yeah.
Okay.
Okay. So there's a question in chat now. How do you know when you're allowed to argue by path induction we can reduce to reflexivity? Well, as long as one endpoint of the path I'm talking about is free, then I'm allowed to argue like this. But that is the answer. And in this case, so at this point where I've underlined here, we need to show that, maybe I'll write that out. So here, the goal is A comma refl A is equal to X comma P. And in this goal, how can I say this? So in the context, the A is before the X and the P, and the X and the P together form a path with a free endpoint. The X is free in P, so I can induct. Yeah.
And the A refl X equal to XP, that stands in for like the DXP. That's the dependent family that you would use.
That's correct. That's correct. So this is DXP. Yeah, that's another way to see that X and P are variable in this type family, whereas A is fixed. You see that D doesn't depend on A. Okay. So that was a good comment. Any final questions about 4 before we move on? So let me comment one last thing about 4. 4 says that if we take the space interpretation of paths,
it says that this, if I fix a base point in some space, then the space of paths starting at that base point is contractible, meaning contractible in the usual topological sense. And we will later see a notion of contractibility in type theory, which, and this type here, essentially the proof we just gave will be showing that this type is contractible. And what does it mean to be contractible? It means you're equivalent to the unit type or the singleton type. And what's the induction principle of the singleton type? Well, you just need to say where the one element goes. And under this equivalence, reflexivity corresponds to that one element. So the reason you can path induct is because as a path with one endpoint fixed, reflexivity is essentially the unique path. And so if I say where it goes, everything else follows. Okay.
And when you say the type is contractible, you're talking about the sigma type.
Yeah, this
that's
sigma
what's
type.
contractible.
Correct.
Okay.
Yeah. So this is the contractible type. So when a term is on the left of the turnstile, it's free. No, not quite, because the A will be on the left of the turnstile. It is in context, but it is not bound in this type family here, or the type family doesn't depend on it explicitly. So it's a bit more subtle than that, unfortunately. Okay, we need to keep moving. So I'll move quickly through this 5 with some sleight of hand. It's written out quite carefully or quite explicitly, so I'll be a bit less careful. So we're going to consider 2 paths, x is equal to y, and q, y is equal to z, in A, some type A. And I'm going to write 3 definitions of a concatenation function. And I'll apply some sleight of hand here and explain, and hopefully you'll follow me. So these 2 paths, if I induct on one, then that doesn't make the other 2 a loop. So it's fine to induct on both. So I'm going to define concatenation 1, the first concatenation operation, which is how we defined it in class. Or actually, yeah, well, scratch that. I don't think it's how it was defined in class in the end. But you can define the first concatenation operation like this. So we take reflexivity, we induct on both P and Q, and then we need to say where the 2 reflexivity paths go. And well, I'm going to say it goes to reflexivity at X. Now, an alternative definition is to say, to just induct on P and let Q still exist. And then you define it to be Q. So this here was a path in X equals X. But once you induct on P, you need to supply a term of type Y equals Z. And you already have such a term, it's Q. So this is Y equals Z. So there's some induction going on in the background, which is letting me change the output type. I hope that this is reasonable to follow. And the third one is where you induct on Q and not P. And then if you induct on Q, then Y and Z become the same, and you need to supply a term of type X equals Y or X equals Z. Well, that's just P. So this is X equals Z. I guess I should write.
Wouldn't in concat 3 it be RY, reflexivity on Y, concatenating?
Yeah. Good catch.
And then the type would be X to Y.
Yeah, but y is equal to z. So
well, yeah, okay, true.
Yeah. So this good catch, reflexivity at y. I guess let's do that because maybe it's less confusing. So then we have three definitions of concatenation. They're not the same. They're not definitionally the same. So that's kind of weird. We have this notion of paths, and we have seemingly three ways of concatenating them. So this is the first one is sort of the unbiased definition. It doesn't prefer P to Q or Q to P, whereas the second one prefers one or the other, and the third one has also sort of a handedness preference. So for this unbiasedness reason, a lot of people prefer one, and that's often what you see in the books. But definitions 2 and 3 have the advantage that they actually compute. So in the sense that reflexivity is a strict left inverse to this if you use concat 2, and reflexivity is a strict right inverse if you use concat 3. So this can come up in formalizing things, that it's handy to have strict computation principles, whereas concat 1 only computes once you give it two reflexivity terms. It's a distinction that comes up. But the important thing is that we can show that they're equal, all these concatenation operations. And does anyone have two favorite numbers, I and j? Don't be shy.
2 and 3, because they're the only primes.
Good. Okay. So our favorite numbers are 2 and 3. So I is equal to 2. J is equal to 3. And now we're going to show that concat 2 is equal to concat 3. And so we want to show that for all P, for all Q, and now I'm moving a bit more quickly here, PQ is equal to concat 3 now, PQ. Okay, but by what we discussed earlier, if I induct on P, that's not going to make Q into a loop. And so I can induct on Q afterwards. And by inducting on P and Q, the goal reduces to the following. On P and Q, the goal is so then we're concatenating with two reflexivity paths. So concat 2 Rx, Rx, concat 3 Rx, Rx. But this just computes by what we discussed above. Concat 2, it even computed before we inducted on both paths. We only needed to induct on the left argument. So this computes to Rx. And the right-hand side, it computes once you've inducted on the right argument. And so this is Rx. And so we can supply a term of this type, which is Rx. And that proves that these concatenation operations are equal in type theory. Okay, so there's a question about intuition. Does the type of equalities A equals B, similar to the set of isomorphisms A, B? There is a relation, but so for a general, well, I mean, so if you're very sophisticated, a type is a so-called infinity groupoid. And a path in an infinity groupoid, if you call it a path or you call it an isomorphism, well, maybe you should call it an equivalence, then the notions are sort of the same, but maybe what you're more looking for, so when you say isomorphism, isomorphism is usually stricter than equivalence. And it makes me think of isomorphisms between set-based objects. And so I think giving a proper answer to this question is a bit beyond the scope right now. So maybe ask that question on the Discord again. Infinity groupoid is a Kahn complex. Yeah, that's a model for it. Books on this perspective. Well, I would say continue reading homotopy type theory. Somehow, homotopy type theory is infinity groupoid theory in disguise. So I would say that's the best way to get intuition and a handle on those things. But you could ask on the Discord, and there might be other thoughts as well.
Question about the equivalence between concat2 and concat3. Logically, the steps made sense, but I was trying to think of it in terms of its homotopy interpretation, where it seems like the different definitions of concat are different ways of contracting two paths that are joined head to tail onto each other somehow, but like concat2 is contracting down to the second path, and concat3 is contracting down to the first path. And so is the final proof that a loop at the very beginning of the path is contractable from I got lost. Could you maybe explain the intuition behind that behind this proof in that interpretation maybe?
Right. So let's see. And I vaguely, so I don't think the interpretation is quite correct because we're constructing a function here. And so concat is not really doing any contraction. I kind of see where you get that intuition from, but it's not really doing any contraction. Rather, yeah, it's a bit hard to explain. Let's see. So if you fix X and you think of, you have first this path P that has a free endpoint Y, and then there's another path that's further out along that from Y, that's Q. The path Q is sort of attached to Y. And now you can do, so as a composed path, well, it's not formally valid either, but maybe it's an intuitive version that might help you. You could sort of think of doing path induction on the whole thing, where you contract both paths to reflexivity and then send them wherever they need to go. And or you could consider doing it in steps. So you contract Q first, and then you say where it needs to go, or you contract P, and then you say where it needs to go. Maybe that's a different way of seeing it.
I was thinking too, each concat2 and concat3, they're both going to be equal to concat1, obviously, right?
That's true, yeah.
So I was just thinking, if you start with concat2, just contract Q and you're going to end up with concat1. And if you start with 3, contract P and you'll end up with cat1, and then just use the transitivity thing. I mean, that's kind of the idea, I feel like because they're both equal
that's
at the
right.
end of the
So
day.
that's good. That's
like
good. Yeah. So that way we can prove that they're all equal. Yeah.
Right.
I see. Okay. So when you're saying contract, you mean induct essentially in the proof.
Yeah, I think that's kind of what he was saying, maybe.
Yeah.
But I didn't, or they were saying, I don't mean to assume, but.
Yeah, no, I get it. But to me, it doesn't make sense to contract a path when you're discussing how to compose them. It does make sense to induct on a path if you're discussing how to compose them.
Yeah, I probably just used improper terminology there. Sorry.
No worries, no worries.
But so concat is a function that can take two arbitrary paths as long as their types indicate that the head of one is the tail of the other, right?
Exactly. Yeah.
So if we were in an interesting space where it's not simply connected,
right.
So you could give two paths to concat, where the concatenation of those two paths forms a non-trivial loop around the space. Yeah.
Absolutely. Yeah.
But then we proved one of these versions of concat by saying that path is going to be equivalent to reflexivity, which implies that there's a way to, I'm not sure if contract is the right word here, but contract that loop down to the point which obviously
yeah. So just because you can eliminate and say where any path goes because you know where reflexivity goes does not imply that every path is reflexivity or equal to reflexivity in any sense. So there will be loops that are not equal to reflexivity, and this will come up shortly and we'll be discussing the circle soon in the course, and the circle will have non-trivial loops and you'll be able to compose them, and we'll compute the fundamental group of the circle. But this it's a remarkable thing that even the behavior of loops is somehow determined by reflexivity as well, just not it's a bit hard to convey. They're not equal. They're not all equal to reflexivity.
So a proof by path induction isn't like encoding some idea, which is what they were saying about being able to shrink paths down. That's not what that is doing.
If the other endpoint is free, then that's a valid intuition.
Okay.
But if the other endpoint isn't free, then you can't shrink a path because the space might not be simply connected.
Exactly.
No. I mean, since you guys seem to be into homotopy stuff, so this if A is an element in a space, is a point in a space big A, then this is what we would call A equals A is the loop space. And that's what models homotopically the loop space of an ordinary space. So if you take the path components of the loop space, you get the fundamental group. Okay, so let's try discussing the last exercise 6, which gets into all these things we've been discussing. So the question now is, if we're given an element of a type A, try constructing a term of the following type. So for all loops at small a, that P is equal to REFL in the loop space. And if you can't construct it, then why not? And the first thing to notice is that we can't apply path induction because both endpoints of P are fixed here. It doesn't have a free endpoint. And so we can't apply path induction, but that doesn't mean there's not some other clever way of constructing a term of this type. There could be. And
And before, so if you assume certain axioms, like something called axiom K, then you can prove this. But if you don't, if you assume univalence, then you can prove that this is false. And we'll see that later in this the course, because this statement says that all loops are equal to REFL in this loop space, but via the space interpretation, there are spaces with non-trivial loops, the non-simply connected spaces, namely. And so the statement will be false for those spaces if A is a simply connected space. And so we will not be able to construct a term. We can actually show that there is no term of this type. Okay, so that's it. That's all I'm going to say about the exercises. I'll stick around to answer any last questions. And I'm trying to catch up on the chat here. Yeah, so somebody says that the free path space where you have, well, depends, you have to say if are you considering one endpoint fixed or not, but what's said here is that the free path space in usual topology contracts to the constant path that translates to path induction. Yeah, that's correct. And it's true that the free loop space isn't contractible either, but this is an actual loop space. It's not a free loop space, but it's true. You can define free loop spaces as well. So you could define Lx. This is the loop space of X if X is a type, and that's the sigma type over all small x in large X, like this. That's the free loop space. How do we show a type is uninhabited? By constructing a contradiction that results in the empty type being inhabited. Yeah, exactly. So you show that this thing implies false, in fact. So that's the only way in type theory. You could also construct a meta proof that says that this type cannot have any inhabitants, but so there's also a meta theoretic way of proving that. But in this case, we can actually show internally in type theory that this implies false, which is an even stronger thing. So you're asking if there are any recipes for showing non-inhabitedness in the meta theory. So this is not my area of expertise. You can ask on the Discord, but for example, you can induct on syntax and do things like this to say that. I mean, yeah, I think that's my answer. Proving non-existence in general is quite subtle. Okay, well, I'm gonna call it. I'm gonna at least stop the recording. So let's see. There we go.